Hello guys, this is the exam review for the first exam in contemporary mathematics. First, I remind you, please take the practice test on Proctorio. If you have never used Proctorio, it is very important to check that your computer allow Proctorio, or maybe you have to change some settings, and it is important that you make a practice test, and then you will better know what to expect from the real test. Okay, the first problem will be from logic, and we know the truth values of two of the variables, and we want to know the truth value of the expression. So we know that P is true and Q represents a false statement, Q is false, and we want to know the truth value of the following expression: that is not true, that not P or not Q. So you will have something similar to this. Okay, if P is true, then not P is false, just the opposite. Q is false, then its negation must be true. So in the parentheses, we have disjunction of true and false. So we have false or true. Or is only false and both are false. Here we have one true value. So or will be true. So this is the truth value inside the parentheses, and outside the parentheses we have a negation sign. So negation of true will be false. So the answer is false. So it doesn't matter which letters do you use, uppercase or lowercase, just write true or false. Okay, and the second part of the question, what is the truth value of the same statement if both P and Q are false? So P is false and Q is false. We find the truth value of the same statement, not P or not Q. So P is false, so not Q is true. Q is false, not Q is true. We have true or true. In the parentheses, we have also true. And then we have a negation. We negate this truth value and we get false. So in this case, when both are false, the answer is also false. The second problem, construct a truth table. Here you will have only one truth table. So I give you two variants just to show that it can be either conditional or biconditional. So let us do truth table for conditional first. So we have a column for P, the column for Q. They are already there. T, T, F, F. And for Q, T, F, T, F. Then we need a column for not P. Not P is the opposite of P. We look at the column for P and write the opposite value. True becomes false, false, and false becomes true. Okay, and then we need a truth value for not P. If not P, then Q. So in this example, it's a little bit not convenient since our hypothesis is on the second place and the conclusion on the left. So I try to give you the examples on the test so that you won't have the situation. You will have hypothesis on the left and conclusion on the right, so that it will be easier. So in our case, hypothesis on the right, and conditional is only false if we have this situation. If true, then false. Any other situation, conditional is true. So if the hypothesis is false, so in the first two lines, conditional is true. If both hypothesis and conclusion are true, conditional is true. Only in the last line we have hypothesis true, conclusion false. We have this situation, if true then false. So we have false in the last cell. Okay, now B. So we start as usual from the same two columns. T, T, F, F, T, F, T, F. And here we need both. We will need not Q and not P. So not Q, we take the opposite of Q. T becomes F, F becomes T. And not P, we take the opposite of P. So P becomes false, T becomes false, false becomes T. And the last column, not Q, if and only if, not P. So if and only if is true when both on the right and on the left truth values are the same. For example, in the first line, we have false and false. They are the same, biconditional is true. In the second line, we have true, false. They're different, biconditional, false. Third line, false, true, false. Last line, both are true, so they're the same, biconditional is true. Okay, so you will fill out one of such tables. In the next example, I have here 4 different examples on the view, but you will have only one. Okay, and you will have multiple choice here. You will have to answer giving the form of this argument and stating whether it's valid or invalid. Okay, so first we must represent it, the statement as in symbolic form. If it snows, let us call this P, then email stays inside. Let's call it Q. If P, then Q. It does not snow. So P is it snows. So the second premise is not P. It doesn't snow. Therefore, email does not stay inside. So he stays inside is Q. So we have here not Q. And now let us look through these tables. You don't have to remember all the names, but you will have this both tables in your instruction field. If P then Q, so the first, the negation of the first and the conclusion is the second. Yes, the negation of the first is fallacy of the inverse. Yes, you choose fallacy of the inverse and fallacy of the inverse. So in this table, and does not tell whether it is valid on the invalid, but you can remember that, and it is invalid. Okay, the second one, if it's the first premise is the same, if P then Q, it does snow, so it is P, therefore Q. So it is law of detachment. And it is valid. The next one, if it snows, then Emil stays inside. The same, start with the same. If P, then Q. Emil stays inside is Q, is the second statement. Therefore, P. So it is a little different. Now the second premise is the second statement from the first premise. So if P, then Q, Q, P. fallacy of converse. And also from the name, you see fallacy must be invalid. Okay, and the last one, so you have one of such variations. If it snows, then Emily stays inside. So if P, then Q. Emily doesn't stay inside, not Q. Therefore it doesn't snow, not P. So this is important to represent, to give it a correct form, symbolic form. Okay, if P then Q, not Q. This is the law of contraposition. And this is valid. Okay. So the next problem, it will also contain only one question, one syllogism, and you will have to draw a picture representing this syllogism and state valid or invalid. So if it is valid, usually only one way how to represent the premises, and they will imply the conclusion. If it is invalid, you must show this one picture that shows that premises can be satisfied, and that imply that conclusion is not satisfied. So actually the answer must contain one picture, either showing it valid and there are no other way to show it, or showing that it is invalid. Okay, every orange is fruit. So actually for every is another word for all, meaning that all oranges must be inside of fruits. So this is the first premise. So both premises must be represented on the same diagram. Don't draw them separate. You can draw it separately for yourself, but the answer must contain both premises on the same diagram. Some fruits are sweet. So we have a circle for sweet. It can be put somewhere touching, overlapping with fruits, but let us look at the conclusion. Some oranges are sweet. Okay. We can prove it invalid by putting sweet, so that the premise is good, satisfied. Some fruits are sweet, but some oranges are sweet is wrong. So the syllogism is invalid. So the second example, we have the same first sentence. Oranges are fruits. So oranges are inside of fruit. But the conclusion is some oranges are not sweet. We can also prove that it is invalid. We can prove that the syllogism is invalid if we draw the circle for sweet, including oranges. So the second premise, some fruits are sweet, is still good, but some oranges are not sweet, is wrong. So the syllogism is also invalid. And the third one, every bird can fly. So every is the same as all. All birds can fly. So birds must be inside of flying. And some mice can fly. So the circle, we will have a circle for mice. And it must be overlapping or completely inside or partially overlapping with flying. But we want to show that maybe some mice are birds. So then we put our circle for mice so that it doesn't touch birds. So the circle for mice is overlapping with flying. So we have shown the second premise very good. Some mice can fly, but it doesn't overlap with birds. So it shows that the conclusion is not true. So the syllogism is invalid. The question with graphs. First question, count the number of edges, the number of lines. So be careful, count them carefully. So the edges are the lines connecting the vertices. We have 3 on the top, 1, 2, 3, 4 in the left square, and we have not count 3 from the right square, plus another 3. 10 edges. The number of the vertices. The vertices are these points, these dots. Yes, we count them. So there are 6 and 1 on the top. Altogether, they are 7. The number of odd vertices. For this purpose, we need to find the degree of every vertex. So A have 3 lines connected to it, 1, 2, and 3. So the degree is 3. 3 is an odd number. B has also 3 lines, 1, 2, and 3. So the degree is 3, and it is an odd number. D, the same thing, 3 lines, the degree is 3, it is an odd vertex. E, only 2 lines, 1, 2, 2 lines, so the degree is 2, and this is an even number, an even vertex. F, 1, 2, and 3, so the degree is 3, 3 is an odd number, so F is an odd vertex. And G is also even. So the degree is 2, is an even number, and G is even. So how many odd vertices? We have 1, 2. I think I forgot C. So C has 4 lines, so the degree of C is 4, and this is an even number. Okay. So we have 1, 2, 3, 4 odd vertices, and even 1, 2, 3 even. And let us check. 4 plus 3 is 7. So we have found them all. So the sum must be the same as the total number of vertices, of course. So if there are no, there are too many odd vertices, then there's no Euler circuit or even Euler path. And if we want to make graph Eulerian, we can add some vertices, and we can add vertices connecting, we can add edges connecting odd vertices. Yes, so in your examples, on the test, you will have only one pair of odd vertices that you will have to connect. Here, in this review example, there are actually 4 odd vertices, so we will have to add 2 different edges, and there are several ways how to do this, so it will be easier on the test. So we can connect A and B, A, B, and there are another pair of odd vertices, D and F, D, F. So if we add these 2 edges, then the graph will be Eulerian and we'll have only even vertices. Okay. The next question, nearest neighbor and best edge. You have to apply both algorithms to the same graph, and it will tell you from what vertex you have to start list vertices. And so first, nearest neighbor. We start from the vertex B. Let us make a small sketch here so that we can see our movements. From vertex B, we have 4 choices. We can go to any of the vertices. And these choices from B are 32, 54. You will have smaller numbers from 1 to 12 or to 15. So 54, 31, and 34. So 31 is the best choice. So we go to D. We go to D. You type D in the blank. So you will type one letter per blank. And you will calculate the weight for this circuit. So the 31. The next choice. So from D, you have three choices. 30. Or you cannot return to B, of course. You can go to A or to E with 35. And DA is the best alternative here, so we move to A. We add 6 to our circuit and we write A in the next blank. From A, you have two choices, either to C or to E. Either 27 or 42. 27 is better, so you move to C. C, and you add 27 to your sum. From C, you actually don't have any choice. Now, so you can only go to E and return to B. Don't forget this last edge. So you add 63, and you add 50, 54. So, and you write the answer to the weight of the circuit. And here from C, we go to E and return to B. There are 5 places, 5 letters. The first letter is already written, and you have to write 5 other letters to make this circuit. Okay. So this the nearest neighbor algorithm is when you move without lifting your pencil from you. When you choose the next vertex, you do not lift your pencil. You just continue moving, move on and move on from vertex to vertex. Okay, now the best edge. The best edge algorithm here, you don't have to find the weight of the algorithm of the circuit. For this algorithm, making a small sketch is necessary. It is very hard to find the answer without this. So let us also add the letter names here. Okay, so you can make a list of all your vertices if it is convenient for you, so that you don't skip anybody. So 6, 27, 30, 30, then 31, then 30, we have 32, 34, 35, 42, and 54, and 63. Okay, we have 10 edges, that's good, all are there. And we start from the very best of them. The best has the weight 6, and this is AD. This is the first edge we choose. The second, with the weight 27, is the edge AC. The third, with the weight 30, is CD, and we cannot choose it. We cannot choose this edge. The fourth to try is BD. BD is good. So if you choose CD, you will finish your circle without visiting B and E. Yes, that's why it doesn't work, but BD is good. With 31, the next 32 is BA. We cannot take it because then we get 3 edges coming to A, so it doesn't work. for Hamilton circuit. We visit every vertex only once. So we don't take 32. 34 BC does not work because then we close the circuit without visiting E. 35 ED does not work because then we will have 3 lines ended at D. So 42 also doesn't work. The last two that we take are 54 and 63. So actually you could see it from earlier, because when we have already 3 edges, often the last 2 are the only possibility. This is the only possibility to finish your circuit. And now we must list the vertices starting from C. Okay, so it will be already written the C, and you will have 5 spaces to fill. So, and there are 2 ways how to write the circuit. If we can go from C to A, then from A to D, from D to B, from B to E, from E return to C. So, or there is another way that will be also correct. You can move in the opposite direction. C, E, B, D, A, C. This is also correct. And directed graph problem. So construct a table that displays the number of directed paths of the length 1 or 2 between each pair of vertices in the graph shown. So just look very carefully and don't skip any connection. So in the first line, we count the ways of the length 1 or 2 from A. From A to B, we can come actually only in one way. A to D, from D to B, 1. From A to C, we don't have any path from A to C, we write 0 here. From A to D, there's only one way directly from A to D. We cannot come to D any other than through E or through B, so only one. From A to E, there are 2 ways, directly AE or ADE, so 2 paths. From B to A, there is no way to come at in 3. Yes, no, there are no way at all to come to A. Actually, you can come to A from any other point because there are no edges coming to A. You can draw zeros here. From B to C, there is only one way how to come there. From E to D, you can go through C. B, C, D, one way. From B to E, B, C, E, one way. From C to B, C, D, B, one way. From C to D, also only one way. From C, you can go either to D or to E, but you can go ED. So there is only one way. From C to E, look, from C, you have 2 edges going out from C, and both of them can lead to E. So there are 2 ways from C to E. From D, DB, one way. So you look on the edges that come out of D. Yes, there are 2 and only one of them comes to B. From D to C. So look, DB, BC, just one way. DE, no way to come to C, so that doesn't work. From D to E, only one way. From E to B, so actually from E, there are no edges coming out from E, so you can go to any other vertex starting from E. So this is the way how to fill out this table. Just be careful by searching for the possible ways. And one more question. Use a given assumption to deduce the truth value for P. So you will have, again, only one of these. So for example, if not Q, then Q and P. And this is false. You know that conditional is only false if it has the form if true, then false. It means that this must be true and this must be false. Then the conditional will be false. So you can actually deduce the truth value of Q. So from the left part, you know that Q is false. And from the right part, you have and here. You know that Q is false, so and will be false for both values. So P may be either false or true. So there will be an option true, choose between true, false, or true or false. So P can be true or false. Because if Q is false, then it doesn't matter if true or false, is P true or false, the and will be false. Not if not Q, then Q or P. And you know that this is false. It means that this must be true and right part must be false. So then you know that Q is false, the same as in the first example. And the difference is that here we have or disjunction. And you know that Q is false in this disjunction. For disjunction, for or to be false, you need that both must be false. So here in this example, P must be false. So here P must be false. Okay. So you will have this table for truth values and this reminder about what is Euler path, what is Hamilton path on your formula sheet, together with this table for law of detachment and so on that we use for one of the problems. You can also use one small sheet of paper with your own notes, a half of the normal paper sheet, and so you actually don't need a calculator, but if you have to calculate a path, you can use a calculator. But if you use your calculator, please show it to Proctorer. I remind you, don't forget to make a Proctorer practice test so that when the real exam starts, you are ready and your computer is ready. Often exam ask you to input password, press on secure proctoring tool in the same folder as your exam. It usually solves the issue very quickly. You just reinstall Proctoring's extension and that's all. Okay, if you have any question, please contact me and I wish you good luck on the exam.